Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. Pierre-Simon Laplace, a name synonymous with scientific brilliance and mathematical innovation, emerged during an era of profound intellectual transformation. His ascent in the world of mathematics was meteoric, a testament to his innate genius, even in the absence of traditional academic validation. One might envision the young Laplace, fueled by insatiable curiosity, grappling with the intricate dance of celestial bodies, seeking to unravel the mysteries that had captivated astronomers and mathematicians for centuries. His early investigations into the motions of planets, moons, and comets quickly established him as a force to be reckoned with. These early efforts, focused on the seemingly intractable problems of celestial mechanics, foreshadowed the breadth and depth of his future contributions. He would go on to leave an indelible mark on not only astronomy, but also probability theory and mathematical physics, areas that might seem disparate at first glance, yet were all profoundly intertwined through the lens of Laplace's analytical mind. This essay aims to explore the remarkable range of Laplace's scientific achievements, tracing his intellectual journey from his early struggles to his eventual triumphs. We will delve into the core of his groundbreaking work, examining the specific challenges he confronted, the innovative solutions he devised, and the lasting impact his ideas continue to exert on modern science. Laplace's contributions to celestial mechanics are perhaps his most widely recognized. The stability of the solar system, a question that had plagued scientists since Newton, found a compelling answer in Laplace's rigorous mathematical analysis. Newton's laws of motion and universal gravitation provided a framework for understanding the interactions of celestial bodies, yet precise predictions remained elusive. The observed movements of planets didn't perfectly align with Newton's initial calculations, giving rise to concerns about the long-term stability of the solar system. Would these deviations accumulate over time, eventually leading to catastrophic collisions or the ejection of planets from their orbits? Laplace tackled this problem head-on, employing advanced mathematical techniques to demonstrate that the perturbations in planetary orbits were periodic and bounded. This was a monumental achievement, offering reassurance that the solar system, while dynamic and complex, possessed an inherent stability. His work provided a profound understanding of the delicate balance of gravitational forces that govern the movements of celestial bodies. Beyond his contributions to celestial mechanics, Laplace revolutionized the field of probability theory. He transformed it from a collection of ad hoc methods into a systematic and rigorous discipline, providing a framework for quantifying uncertainty and making informed decisions in the face of incomplete information. Laplace's work on probability laid the foundation for modern statistics, risk assessment, and decision theory, finding applications in fields ranging from finance to medicine. His treatise on probability stands as a testament to his intellectual prowess, presenting a comprehensive and unified treatment of the subject. He introduced key concepts such as the principle of indifference, which provides a foundation for assigning probabilities in the absence of specific information. He also developed powerful techniques for calculating probabilities in complex scenarios, including the use of generating functions and asymptotic approximations. Furthermore, Laplace made significant contributions to mathematical physics, applying his analytical skills to a wide range of problems in areas such as heat transfer, acoustics, and fluid dynamics. His work in these areas demonstrated the power of mathematics to model and understand physical phenomena, paving the way for new discoveries and technological advancements. One of his most enduring contributions to mathematical physics is the Laplace transform. This mathematical tool, which transforms a function of time into a function of frequency, has become an indispensable tool for solving differential equations that arise in a wide variety of engineering and scientific applications. The Laplace transform, initially conceived as a method for solving linear differential equations with constant coefficients, has evolved into a powerful analytical tool with far-reaching applications. It simplifies the process of solving differential equations by transforming them into algebraic equations, which are often easier to solve. Once the algebraic equation has been solved, the inverse Laplace transform can be used to recover the solution to the original differential equation. The initial impact of the Laplace transform was immediate and profound. Engineers and physicists quickly recognized its potential for solving a wide range of problems in areas such as circuit analysis, control systems, and signal processing. The Laplace transform provided a systematic and efficient way to analyze the behavior of these systems, enabling engineers to design more effective and reliable devices. The Laplace transform also found applications in other areas of science and mathematics. For example, it has been used to solve partial differential equations that arise in heat transfer and fluid dynamics. It has also been used to analyze the stability of dynamical systems and to study the properties of probability distributions. The Laplace transform continues to be an active area of research, with new applications and extensions being developed all the time. Its enduring relevance is a testament to the power and elegance of Laplace's original ideas. The story of Aristide Galois is one of both brilliance and tragedy. His life was marked by political turmoil, academic setbacks, and ultimately a premature death. His mathematical ideas, initially rejected and misunderstood, were only fully appreciated after his passing. Today, Galois theory stands as a testament to his extraordinary genius, a cornerstone of modern algebra and a powerful tool for understanding the fundamental nature of mathematical structures. This essay will explore the life and work of Aristide Galois, tracing his intellectual journey from his early mathematical explorations to his groundbreaking theory of solvability by radicals. It will delve into the mathematical concepts underlying Galois theory, providing a clear and accessible explanation of his group-theoretic approach to polynomial equations. Furthermore, it will examine the historical context in which Galois developed his ideas, highlighting the challenges he faced in gaining recognition for his work. It will also discuss the profound impact of Galois theory on the development of modern mathematics, illustrating its enduring relevance and its connections to other areas of science and technology. We will begin by examining Galois' early life and education, exploring the factors that shaped his mathematical development and the obstacles he encountered in his pursuit of knowledge. We will then turn to a detailed analysis of his mathematical contributions, focusing on his theory of solvability by radicals and the underlying concepts of group theory. We will explain how Galois associated a group with each polynomial equation and how the structure of this group determines the equation's solvability. Following this, we will delve into the reception of Galois' work by the mathematical community, examining the reasons for its initial rejection and the subsequent recognition of its significance. The mathematics that allows us to decompose complex functions into simpler components, making them easier to analyze and manipulate, remains a cornerstone of modern engineering and scientific analysis. Laplace's intellectual curiosity knew no bounds. He approached scientific problems with a rare combination of mathematical rigor, physical intuition, and philosophical insight. His work exemplified the power of interdisciplinary thinking, demonstrating how mathematical tools could be applied to solve problems in a wide range of scientific disciplines. His legacy extends far beyond his specific discoveries, inspiring generations of scientists and mathematicians to pursue knowledge with the same passion and dedication that characterized his own remarkable career. He truly shaped our understanding of the world. Having exerted such a profound influence on analysis and mathematical transformations, Laplace turned his formidable intellect towards the heavens, seeking to unravel the mysteries of celestial motion. His investigation into celestial mechanics represented another monumental chapter in his scientific career, one that addressed fundamental questions about the stability of the solar system and the very origins of planetary bodies. The late 18th and early 19th centuries saw astronomers grappling with discrepancies between Newtonian gravitational theory and observed planetary movements. While Newton's law of universal gravitation provided a remarkably accurate framework for understanding the interactions between celestial objects, it seemed unable to fully account for certain subtle, yet persistent, variations in the orbits of planets. These deviations, often referred to as perturbations, posed a significant challenge to the prevailing scientific understanding. The problem, in essence, was this: Newton's equations perfectly described the motion of two bodies interacting gravitationally. He demonstrated that the perturbations in the orbits of Jupiter and Saturn, the two largest planets in the solar system, were periodic and bounded. This meant that while the orbits of these planets did fluctuate over time, these fluctuations remained within certain limits and did not lead to a continuous, unbounded increase in the orbital parameters. In other words, the planets would not spiral into the Sun, collide with each other, or be ejected from the solar system. Laplace's proof relied on a careful analysis of the gravitational interactions between Jupiter and Saturn. He showed that the exchange of energy between these two planets, caused by their mutual gravitational attraction, resulted in periodic variations in their orbital elements. These variations, while significant, were ultimately self-correcting, preventing any long-term instability. This discovery was a major triumph for Newtonian mechanics and provided strong evidence for the inherent stability of the solar system. It addressed the concerns of his time by offering a purely mechanical explanation for the observed planetary movements, obviating the need for divine intervention. The key to Laplace's success lay in his innovative mathematical techniques. He developed perturbation theory to an unprecedented level of sophistication, allowing him to approximate the solutions of complex differential equations that described the motion of planets. He introduced new mathematical tools and methods that became essential for subsequent work in celestial mechanics. His work provided a rigorous foundation for understanding the long-term behavior of planetary systems and paved the way for future investigations into the dynamics of the solar system. Beyond his work on the stability of the solar system, Laplace also made significant contributions to our understanding of its origins. He is best known for his nebular hypothesis, a theory that proposed that the solar system formed from a rotating cloud of gas and dust. This hypothesis, first outlined in his book Exposition du Système du Monde, offered a compelling explanation for the observed characteristics of the solar system, such as the nearly coplanar orbits of the planets and their common direction of revolution around the Sun. According to the nebular hypothesis, the solar system began as a large diffuse cloud of gas and dust, slowly rotating in space. Over time, this cloud began to collapse under its own gravity, causing it to spin faster and flatten into a disk. As the cloud continued to contract, most of the mass concentrated at the center, forming the Sun. The remaining material in the disk gradually coalesced to form the planets, moons, asteroids, and other objects in the solar system. The nebular hypothesis provided a unified and coherent explanation for the formation of the solar system based on the laws of physics and the principles of gravitational attraction. It offered an alternative to earlier creationist accounts and marked a significant step forward in our understanding of the origins of planetary systems. While the original nebular hypothesis has been refined and modified over time,
its basic principles remain a cornerstone of modern theories of planet formation. Laplace's contributions to celestial mechanics laid the groundwork for modern astrophysics. His mathematical techniques for analyzing planetary motion are still used today by astronomers and astrophysicists to study the dynamics of the solar system and other planetary systems. His nebula hypothesis, while not without its limitations, continues to inspire research into the formation and evolution of stars and planets. His work represents a remarkable achievement in the history of science, demonstrating the power of mathematical reasoning and physical intuition to unlock the secrets of the universe. His insights into the stability of planetary orbits and the formation of the solar system shaped our understanding of the cosmos and continue to resonate with scientists and researchers today. The quest to understand the cosmos, exemplified by Laplace's celestial mechanics, represents just one facet of his extraordinary intellectual output. His profound insights were not confined to the predictable clockwork of the heavens, they extended to the inherently uncertain realm of probability. The late 18th and early 19th centuries witnessed a growing need for a robust framework to analyze chance events, inform decision-making in areas ranging from insurance to jurisprudence, and grapple with the inherent uncertainties present in scientific measurement. Existing methods for dealing with probabilistic events, however, were often ad hoc, incomplete, and lacked the rigor necessary for widespread application. Prior to Laplace, the mathematical theory of probability, while having its roots in the 17th century work of figures such as Pascal and Fermat, remained largely fragmented. While these earlier thinkers had addressed specific problems, such as those related to games of chance, a comprehensive, unified theory capable of handling a wide range of real-world situations was conspicuously absent. The absence of standardized techniques and universally accepted principles hindered progress in fields that relied on probabilistic reasoning. Actuarial science, for instance, depended on mortality tables and estimations of life expectancy, but these were often based on limited data and lacked a solid theoretical foundation. Similarly, legal judgments, which sometimes involved assessing the likelihood of certain events, relied on subjective interpretations rather than rigorous quantitative analysis. Scientific endeavors, increasingly reliant on observation and measurement, grappled with the problem of experimental error. How could one separate genuine signals from random noise? How could one combine multiple observations to arrive at the most accurate estimate of a physical quantity? These questions demanded a more sophisticated approach to probability than was currently available. Laplace provided this approach through his contributions to the field. He embarked on a mission to develop a comprehensive theory of probability, one grounded in mathematical principles and capable of addressing a wide range of practical and theoretical challenges. His magnum opus, Théorie analytique des probabilités, stands as a testament to his ambition and intellectual prowess. This monumental work, along with its more accessible introduction, Essai philosophique sur les probabilités, laid the foundation for modern probability theory and statistical inference. One of the cornerstones of Laplace's approach was the principle of indifference, also known as the principle of insufficient reason. This principle states that if there is no reason to believe that one event is more likely than another, then they should be assigned equal probabilities. While seemingly straightforward, the principle of indifference provided a crucial starting point for analyzing situations where prior knowledge was limited. For example, when considering a coin toss, in the absence of any evidence to suggest that the coin is biased, one would assign a probability of 1/2 to the event of heads and 1/2 to the event of tails. This principle allowed Laplace to tackle problems where subjective judgment might otherwise dominate, providing a more objective and mathematically sound basis for probabilistic reasoning. The principle of indifference, it must be noted, is not without its critics. and its application requires careful consideration of the specific context. However, its importance in the historical development of probability theory is undeniable. Laplace also made significant contributions to the problem of statistical inference, the process of drawing conclusions about a population based on a sample of data. One of his most notable achievements in this area was the development of the law of succession, a formula for estimating the probability of a future event based on past observations. The law of succession addresses the question, if an event has occurred n times in a row, what is the probability that it will occur again on the next trial? Laplace derived a formula for this probability, taking into account the uncertainty inherent in extrapolating from limited data. A famous illustration of this law involves the rising of the sun. Given that the sun has risen every day throughout recorded history, what is the probability that it will rise again tomorrow? Laplace's formula provides a quantitative answer to this question, reflecting the overwhelming evidence in favor of the sun's continued regularity. The law of succession, though sometimes debated for its philosophical implications, demonstrated Laplace's ability to translate intuitive notions about probability into precise mathematical expressions. Perhaps Laplace's most enduring contribution to probability theory is his rigorous formulation and extension of the central limit theorem. This theorem, which had been foreshadowed by earlier work of de Moivre, states that the sum of a large number of independent, identically distributed random variables will be approximately normally distributed, regardless of the underlying distribution of the individual variables. The central limit theorem is a cornerstone of modern statistics, providing a powerful tool for approximating probabilities and making inferences about population. Its significance lies in its universality. It applies to a wide range of situations, even when the underlying distributions are unknown or complex. For example, in quality control, the central limit theorem allows engineers to monitor the average weight of manufactured products, even if the individual weights vary randomly. In opinion polling, it allows statisticians to estimate the proportion of voters who support a particular candidate, even if they only survey a small sample of the population. The central limit theorem provides the mathematical justification for using the normal distribution as a workhorse in statistical analysis. Laplace's contribution was to provide a general proof of the theorem, solidifying its theoretical foundation and paving the way for its widespread application. Théorie analytique, de probabilité, extended far beyond these core concepts. It encompassed a wide range of topics, including generating functions, difference equations, and the method of least squares. Laplace developed powerful analytical techniques for solving probabilistic problems, often drawing on his expertise in calculus and differential equations. He demonstrated how these techniques could be applied to diverse areas, from astronomy to demography. The book served as a comprehensive treatise on probability, showcasing the power of mathematical analysis to illuminate the workings of chance. While the Théorie analytique des probabilités is notoriously difficult to read, even for seasoned mathematicians, its influence on the development of probability theory is undeniable. It established a new standard of rigor and sophistication, inspiring generations of mathematicians and statisticians to build upon Laplace's foundations. The book became a touchstone for those seeking to understand the mathematical underpinnings of uncertainty. The impact of Laplace's work on probability theory extends far beyond the confines of academia. His contributions have had a profound influence on a wide range of fields, from finance to medicine. The central limit theorem, in particular, remains an indispensable tool for statistical analysis and decision-making. It is used extensively in data science, where it provides a foundation for many machine learning algorithms. The mathematics that allows insurance companies to bet on our collective longevity and usually win relies directly on the law of large numbers, a close relative of the central limit theorem. Laplace's ideas continue to shape our understanding of uncertainty and our ability to make informed decisions in a complex and ever-changing world. The profound impact of Laplace's probabilistic investigations reverberated through the scientific community, and his analytical prowess soon turned toward another formidable challenge: the solution of differential equations. These equations, fundamental to describing physical processes in fields ranging from mechanics to heat transfer, presented significant hurdles for mathematicians and engineers of the era. Finding solutions, especially for complex systems, often proved elusive, hindering progress in understanding and predicting real-world phenomena. Differential equations, in essence, express relationships between a function and its derivatives. They are the language of change, describing how quantities evolve over time or space. The trajectory of a projectile, the flow of heat through a solid, the vibrations of a string, all are governed by differential equations. However, the task of actually solving these equations, of finding the functions that satisfy them, can be extraordinarily difficult. Analytical solutions, those expressible in terms of familiar mathematical functions, are often unattainable, particularly when dealing with nonlinear equations or complex boundary conditions. Consider the problem of modeling the motion of a damped harmonic oscillator, a system consisting of a mass attached to a spring, subject to frictional forces. The differential equation governing this system involves not only the displacement of the mass, but also its first and second derivatives, representing velocity and acceleration respectively. Finding a function that satisfies this equation, while also adhering to specific initial conditions such as the initial position and velocity of the mass, can be a daunting task using traditional methods. Engineers faced similar challenges in designing and analyzing electrical circuits. The behavior of circuits containing inductors, capacitors, and resistors is also described by differential equations. Determining the current and voltage as functions of time in response to a particular input signal requires solving these equations. The complexity increases dramatically when dealing with circuits containing multiple components or nonlinear elements. Laplace recognized the limitations of existing techniques and sought a more systematic and powerful approach to solving differential equations. His ingenious solution was the development of what is now known as the Laplace transform. This transform provides a method for converting a differential equation in the time domain into an algebraic equation in the frequency domain, where the frequency domain is characterized by the complex variable s. The Laplace transform of a function f of t, typically denoted by capital F of s, is defined as the integral from 0 to infinity of e to the negative s, t multiplied by f of t with respect to t. The beauty of this transformation lies in its ability to convert differentiation into multiplication. Specifically, the Laplace transform of the derivative of a function is equal to s times the Laplace transform of the function minus the initial value of the function. This property allows one to replace derivatives in a differential equation with algebraic expressions involving s, thereby transforming the differential equation into an algebraic one. This algebraic equation, being typically far simpler to solve, can then be manipulated to find the Laplace transform of the solution. Finally, an inverse Laplace transform is applied to obtain the solution in the original time domain. The inverse Laplace transform, while conceptually straightforward, often involves complex integration techniques or the use of pre-computed tables of Laplace transform pairs. The impact of the Laplace transform on solving linear differential equations with constant coefficients was profound. These types of equations arise frequently in physics and engineering, modeling systems with constant parameters. The Laplace transform provided a systematic and efficient method for finding solutions, even for equations of high order or with complex forcing functions. For instance, consider again the damped harmonic oscillator. Applying the Laplace transform to its governing differential equation transforms it into an algebraic equation in SES. Solving this algebraic equation yields an expression for the Laplace transform of the displacement. Taking the inverse Laplace transform then gives the displacement as a function of time, directly revealing the oscillatory behavior and the damping characteristics of the system. Similarly, in circuit analysis, the Laplace transform allows engineers to analyze the transient response of circuits to various input signals. By transforming the circuit equations into the frequency domain, they can determine the impedance of the circuit elements and analyze the circuit's behavior at different frequencies. The inverse Laplace transform then provides the time domain response, revealing how the circuit settles to its steady state. The Laplace transform's utility extends beyond simply finding solutions to differential equations. It also provides valuable insights into the stability and behavior of systems. The poles of the Laplace transform of the solution, which are the values of S that make the denominator of the transform equal to 0, determine the stability of the system. If all the poles lie in the left half of the complex plane, the system is stable, otherwise it is unstable. Furthermore, the Laplace transform facilitates the analysis of systems with discontinuous inputs, such as step functions or impulse functions. These types of inputs are often used to model sudden changes in the system's environment. The Laplace transform handles these discontinuities gracefully, providing accurate solutions even in these challenging scenarios. The development of the Laplace transform revolutionized the field of differential equations, providing a powerful and versatile tool for solving a wide range of problems in physics and engineering. Its influence continues to be felt today, with widespread applications in modern engineering disciplines. In modern engineering, the Laplace transform remains an indispensable tool for a multitude of applications. It is used extensively in control systems engineering, where it facilitates the design and analysis of feedback control loops. Control systems are used to regulate the behavior of dynamic systems, ensuring that they operate within desired specifications. The Laplace transform allows engineers to analyze the stability and performance of control systems and to design controllers that meet specific performance criteria. For example, consider the problem of controlling the temperature of a chemical reactor. The reactor's temperature is influenced by various factors, such as the flow rate of coolant, the rate of chemical reaction, and the ambient temperature. A control system uses feedback to maintain the reactor's temperature at a desired set point. The Laplace transform allows engineers to model the reactor's dynamics, design a controller that compensates for disturbances, and ensure that the closed-loop system is stable and responds quickly to changes in the set point. Another area where the Laplace transform plays a crucial role is in signal processing. Signal processing involves the analysis and manipulation of signals, such as audio signals, images, and communication signals. The Laplace transform is used to analyze the frequency content of signals, design filters that remove unwanted noise, and compress signals for efficient storage and transmission. For instance, in audio processing, the Laplace transform can be used to analyze the frequency spectrum of a musical recording. This information can then be used to design equalization filters that enhance certain frequencies or attenuate others, improving the overall sound quality. Similarly, in image processing, the Laplace transform can be used to detect edges and features in an image, enabling applications such as object recognition and image segmentation. The Laplace transform's influence extends beyond these core areas.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.